In this presentation, we are going to discuss about linear bounded automata. But first, let us go through a brief introduction to the various automata in the theory of computation. According to Chomsky's hierarchy, grammar is divided into four types as follows. Type 0 grammar is known as unrestricted grammar. Type 1 is known as context-sensitive grammar. Type 2 is context-free grammar, and Type 3 is regular grammar. Regular grammar generates regular languages, which are accepted by finite automata. Context-free grammar generates context-free languages, which are accepted by push-down automata. Context-sensitive grammar generates context-sensitive languages, which are accepted by linear-bounded automata. Finally, recursively enumerable grammars are a subset of unrestricted grammars that are restricted to generating only those languages that can be recognized by a Turing machine. So this is a comparison of the various automata based on four parameters: presence of memory in the automata, the data structure implemented by each, the tuple representation, and the grammar accepted by each. In our syllabus, we have covered finite automata, push-down automata, and Turing machines. So let's discuss about linear bounded automata. Linear bounded automata is a type of computational model that operates similarly to a Turing machine, but with limited memory resources. The LBA starts with an input string on the tape, and the head of the tape is initially positioned on the leftmost character of the input string. The LBA reads the input string and uses the transition function to move the head of the tape left or right and change its state. The LBA accepts the input string if it reaches the accepting state and rejects it if it reaches the rejecting state. LBA is equivalent in computational power to deterministic Turing machines, meaning that any language that can be recognized by an LBA can also be recognized by a deterministic Turing machine, and vice versa. However, LBAs have some practical applications, such as in the field of natural language processing, for parsing and analyzing text where input strings are typically of limited length. So these are the various applications of LBA. LBAs can be used in DNA computing, which is a field that uses DNA molecules as a computational substrate. LBAs can be used to model the behavior of DNA molecules and design DNA-based algorithms. LBAs can be used in compiler design to generate intermediate code from source code. Intermediate code is a low-level representation of source code that can be easily translated into machine code. LBAs are used in text processing applications such as search engines and information retrieval systems. They are used to match patterns in text and perform text transformations. Finally, in game theory, LBAs are used to model and analyze interactions between agents. Now, every type of automata can be represented by a tuple. This is the 8-tuple definition of linear bounded automata. Q represents a finite set of transition states. Sigma represents the input alphabet. Delta represents the transition function, which is defined as such. Tau is the tape alphabet. Q0 is the initial state. ML represents the left bound of the tape. MR, the right bound of the tape. And finally, F represents a finite set of final states. Here, L and R specify the left and right movements of the tape head. As discussed previously, linear bounded automata only accept context-sensitive languages, which are defined by context-sensitive grammar. So let us understand what context-sensitive grammar is. Every grammar is defined by a 4-tuple VTSP. Here, V represents the set of variables, T the set of terminal symbols, S the starting symbol of the production, and P the production rules. A context-sensitive grammar is an unrestricted grammar whose production rules are of the form alpha defines beta, such that the length of alpha is less than or greater than equal to the length of beta, and alpha beta are strings of terminals and non-terminals. Here are some sample languages accepted by linear bounded automata. Since these languages are accepted by an LBA, clearly they must be context sensitive. Let's design an LBA for one of the languages listed in the previous slide, namely L is equal to AN, BN, CN, where N is the common constraint and is greater than or equal to 1. This is the basic algorithm or approach that we'll use to proceed with the design of the LBA. We'll consider the sample string AAA, triple B, triple C. Clearly, this string belongs to the language AN, BN, CN. Let's start with the tape movement of the linear bounded automata. Initially, the tape head points to the first symbol of the input string, that is, towards A. We'll mark A as X and move one step right and reach the unmarked B by passing every A on the way to B. Then we'll mark B as Y and move one step right and reach the unmarked C by passing every B on the way to C. Now C is marked as Z and we move one step towards the left because now we have to repeat the process. We reach the unmarked X and pass every Z, B, Y, A on the way to X. And now that we've moved to A, we repeat the process entirely. Lastly, when the tape header reaches X and the next symbol is Y, that means all A's are finished. We check for B's and C's by going towards blank, towards the direction of right, and passing Y and Z on the way. If no B and C are found, that means the string is accepted. We can now draw the state transition diagram for this linear bounded automata. Based on the state transition diagram, we have tabulated the transition function as follows. You might notice that the steps taken to design the LBA were quite similar to those that are required for designing a Turing machine. This is because a linear bounded automata and a Turing machine are quite similar. The LBA has a significant limitation in that it can only use a finite amount of space on the tape. The amount of tape space available to an LBA is proportional to the length of the input string. Specifically, the tape of an LBA has the form of a tape window that can move left or right, but the window cannot exceed the length of the input string. This restriction means that the LBA can only access a constant amount of additional tape space beyond the input string. Here we have shown the differences between an LBA and a Turing machine based on 4 parameters. The limitations of linear bounded automata call for an automata with more power, which brings us to the Turing machine, which has more computational power than any other form of automata. Thank you.